Today I'm going to talk about maximal independent sets in Clique-free graph. Everything I say here is going to be joint work with Shadi P and Josh E. Given a graph G, we say that a set of vertices I is a maximal independent set, which we'll simply abbreviate as an MIS. If I is an independent set, but I together with any other vertex is not an independent set. In other words, every vertex that's not an I has some neighbor in I. Right? This is a fairly natural definition to consider. I'll note that this is considered a decent amount by computer scientists in that community. That's because there are various aspects of MIS that have applications to social network analysis and other fancy words. And because of this, there's a lot of work being done on algorithms for efficiently finding MISs in a given graph. But for us, we're going to focus on the following extremal problem, which broadly speaking says, given a family of graphs G, what's the maximum number of MISs of some graph in this family? So perhaps the simplest case to consider is all n vertex graphs. So we'll let M of n denote the maximum number of MISs that an n vertex graph can have. And a theorem due to Miller and Muller and Moon and Moser independently determined M of n exactly. And basically the lower bounds from this construction or from this function comes from the following construction, namely take n over 3 disjoint unit, the disjoint unit of n over 3 triangles, at least when n is divisible by 3. If n is not, you do something slightly different, but basically it looks like this. And the observation if we took is that if we take one vertex from each of these triangles, then we get an maximal independent set. It's clearly an independent set because we're taking one vertex from each component. And it's also maximal because we try to add a second vertex in any component, it's already adjacent to something that we put in there. So the number of MISs in this picture is 3 to the n over 3. So that gives the lower bound, and most of the work in these papers is dealing with the upper bound. Right? So this, given this result, we want to ask the following question. If I have a graph G, which is far from this extremal construction of disjoint unit triangles, then how much smaller, how much fewer MISs will it have? Will it still be close to 3 to the n over 3? Will it be something significantly smaller? And here I'm being intentionally vague about what exactly I mean by far from the extremal construction. And there are many different ways you can answer that question. For example, I believe Ferretti has some results dealing with the case that you look at connected graphs. That's one way to be far from a disjoint unit of cliques. But the direction we want to look at is for triangle-free graphs, which again, I hope you all agree is far from a disjoint unit of triangle. So let M3 of n denote the maximum number of MISs that an n-vertex triangle-free graph can have. And this problem in turn was essentially solved by Poiter and Tusa, who determined the function to be exactly this quantity here, where the lower bound comes from either a perfect matching is if n is divisible by 2, or an almost perfect matching together with 1 5 cycle. And that gives the lower bounds here. So again, most of the work is in improving its upper bound. And a couple things to note. First is that indeed the number of MISs here is significantly smaller than the number of MISs here. So it does change, the behavior of the function does change significantly once we look at triangle-free graph. And the other thing to note is that this theorem has seen a lot of use in the past couple of years. In particular, this ended in some variants thereof. For example, it was a key element in the proof in determining the number of maximal triangle-free graphs on n vertices due to Balog and Petrova, as well as counting the number of maximal sum-free subsets of the first n integers. So in addition to just being a nice question to ask in its own right, these sorts of questions do have further applications. So another kind of problem we can look at is a slightly more refined version of the problem we've been talking about. This is counting not only just general MISs, but MISs of a given size k, which we'll refer to as k MISs. And this is partially motivated by, for example, in this Moon and Moser construction of disjoint unit triangles, every MIS is size exactly n for 3. So you could ask, if I only care about MISs of size 17, again, how much does this change the behavior of the function? So let M and K denote the maximum number of KMISs that an n vertex graph can have. And this function was determined by Nielsen, who showed that the extremal construction is a disjoint unit of k cliques, all of size as close to n over k as possible. In other words, this construction is the complement of the Tron graph. And similar to how it went from Moon-Moser to Voigt-Tusa, you can ask, what if we're far? We have a graph G which is far from a disjoint unit of cliques. How much does this m of n and k function change? And that brings us to the central object we have for this talk, which is mt and k, which is the max number of k MISs that an n vertex kt free graph can have. So this is what we want to explore. And given what we've done up to this point, for the first theorem, the extremal example was disjoint union of triangles. Then it was disjoint union of K2s in the case of triangle free graphs. And then it was a disjoint union of cliques for MISs of size K. So motivated by this, we might think that the answer again here is disjoint union of something, which is KT3. And you can play around with this a bit, and I claim that something that'll pop up for too long is what I'm going to refer to as a co-matching. So this is a complete balance by part graph after deleting a maximum size matching. So for example, we're missing this edge and this edge and this edge and this edge and so on and so forth. So a couple observations here. One is that this is a triangle free graph, and in particular, it's KT free for any t greater than or equal to 3. And the number of 2 MISs it has is at least floor n over 2. Because you can go for each of these non-edges across the part. That's an independent set of size 2. More, if we look at any other vertex not there, it's going to be adjacent to the vertex of this set on the opposite side. So it has two MIS for each non-edge, of which there are 4 n over 2. So let's pretend we think this is a good candidate for possibly achieving this extremal value, and let's see how far we can get using these as building blocks. So as mentioned before, they're triangle free graphs which have at least a linear number of 2 MISs. Now, if you want to do with 3 MISs, one thing you can do, so it's not obvious it's the best you can do. In fact, it isn't, but anyway, it's decent. Is you can take a co-matching together with one isolated vertex. Because now any set which consists of this vertex and a non-edge in your co-matching will be 3 MIS. And basically the number of ways to do this is exactly the number of 2 MISs in the co-matching, of which there are about n. And then when k goes up to 4, we can do much better. So here we can take the disjoint unit of 2 co-matchings of the same size. And here, if I look at any non-edge across 2 parts and any non-edge across 2 parts in the other component, this will be 4 MIS. So there's about n squared options. And you kind of keep playing this game and get that for triangle free graphs, you can get graphs which have n to the floor k over 2 k MISs. So that gives triangle free graphs, and these are KT free for any reasonable choice of t. So at this point, you might ask, is that genuinely the best you can do? For any fixed k and t, do we have a matching upper bound of n to the floor k over 2? And for a while, I thought this was the case. And there's some good evidence for this, or some reasonable evidence for this. In particular, for triangle free graphs and 2 MISs, this extremal function is exactly floor n over 2, and moreover, the unique graph which achieves this lower bound is the co-matching of order n. This strongly suggests that, at least for triangle free graphs, if we're going to be the disjoint unit of something, probably it's going to involve co-matching. Moreover, we can prove that the order of magnitude for 3 MISs and 4 MISs is n and n squared respectively. So if you went back to the previous slide, you would see these are exactly the lower bounds that we were able to achieve with these co-matching constructions. So at least for k at most 4, those constructions were the best we could do, and agrees with this question here. However, as you might have picked up, this is not the truth in general. In particular, for KT free graphs with t greater than or equal to 4, The number of 3 MISs, or the maximum number of 3 MISs, is at least n squared minus little o of 1. So for triangle-free graphs, the number of 3 MISs is the most linear. But once you go up to K4-free graphs, you immediately get an extra factor of n, more or less. And the key tool for proving this result is a famous construction of Ruza and Semiramis, which is an n-vertex tripartite graph G, which has n squared minus little 1 edges, and such that every edge is contained in a unique triangle. And given this graph G, we'll define the tripartite complement of G in the following way. So first, we start with G. Then we take the literal graph complement, flip non-edges to edges and edges to non-edges. And in particular, we're going to end up with cliques in the tripartite parts of our vertex set. And then from this graph complement, we'll just delete all the edges in these large cliques. So equivalently, what we're doing is we're just looking at all the edge sets between two parts and then flipping whether they're an edge or non-edge. This is a sort of complement that preserves us being tripartite with respect to this tripartition. All right, so again, this picture. And the claim is if we have a triangle in our original Ruza-Semiramis graph, then we have a 3 MIS in, or that is a 3 MIS now in our tripartite complement. So first of all, it's an independent set because the only way to have triangles here, because we're three-parted, is you have a vertex here, here, and here, and you have edges across all three parts. But now all these edges get flipped off when we take the tripartite complement. Now to deal with maximality, we assume that we could add this extra vertex W prime and still be an independent set. Then you can work through the definitions and see that this means that UV and W prime is itself a triangle in Ruza-Semiramis. But the edge UV is contained in a unique triangle in Ruza-Semiramis. So this third vertex W prime must be the same as this third vertex W. The only way to add a new vertex to our independent set is if we add something that's already in there. So this is indeed maximal independent set. So moreover, so we've proven now that every triangle corresponds to 3 MIS. The Ruza-Semiramis construction contains n squared minus little 1 triangles. And moreover, our graph is going to be KT-free for t greater than or equal to 4, since we're in particular 3 parts. That is the result that's claimed. And you can go through and mimic this proof and find out what would help us improve this n squared to like an n cubed or something like this. And the key thing we need is for the existence of a k-partite n-vertex graph, contains many copies of cliques of size k-1, all of which are contained in a unique clique of size k. So if you plug in k equals 3, this is exactly the parameters of the Ruza-Semiramis construction that we needed. And in fact, if you take k equals 2, this sort of graph here is exactly a perfect matching. And the bipartite complement of a perfect matching is a co-matching. So in many regards, these properties recovers not only this Ruza-Semiramis type construction, but also the co-matching type construction. And fortunately for us, it is known that graphs with these properties exist. In particular, with some recent work of Bowers and Janser, they proved a stronger result, namely that there exists n-vertex graphs which have about n to the L copies of any L clique, they have n to the L copies of L cliques, so that each L clique is in at most one K clique. So for our purposes, we only need the L equals K minus 1 case of this result. And if you again, follow your nose and just replicate exactly what I said in the previous slide, you'll end up getting the following lower bound for MT and K, provided K is strictly smaller than T. And you can push this a little further. And basically by taking disjoint unions of these constructions of Gowers and Janser and co-matchings and Ruza-Semiramis type construction, just taking a bunch of disjoint unions of these, I claim we can get the following lower bound here for any fixed K and T. And again, I'm not going to go through the details because they're not particularly enlightening, but basically this is analogous to when we're just working with co-matchings, we would take, co-matching, then a K1, then a co-matching, then a K1, then a co-matching. Here you would do, for example, Ruza-Semiramis root ephemerate plus K1, root ephemerate plus co-matching, root ephemerate plus root ephemerate, and so on and so forth for K porphyry graphs, and analogous things for KT3 graphs using Gaussian search type constructions. So we can prove this bound, which is much better for a larger T compared to our previous bound of K over 2, which we might have naively thought was the right answer. But still the question remains, are these new bounds best possible? In particular, for triangle-free graphs, is the lower bound we have of n to the 4 K over 2 that we mentioned before best possible? And here, things are starting to look more reasonable because we know it's true for K at most 4. But yet again, it turns out this isn't the case. So there's a lot of things on this slide. So let me go through it slowly. We're going to start with some ambient K cycle, which has some edges and some vertices arranged how they are. And we'll define the blow-up graph GNCK½ as follows. This will be a K partite graph where each blob of vertices, Vi, will consist of all the functions which map the edges EI and EI plus 1 to some integer from 1 to n to the 1/2. So they map each, to be clear, takes in one of 2 inputs and outputs some potentially different 2 numbers in this range. We'll then make 2 functions f in the ith blob adjacent to g in the jth blob if there's an edge between the ith and jth vertex of the graph cycle, i.e. if I and j differ by 1, and if on this common edge containing Vi and Vj, f and g disagree with what the value of E is. That's formally what this definition is. Let's again try and work through things with some pictures. So we start with our ambient C4 in this case, and we're going to make a 4-partite graph that looks kind of like this. It's basically going to be a blow up of C4, but with some edges deleted between parts. And in particular, each vertex in, say, V2 here is some function f, which assigns some value to E2 and assigns some value to E3, maybe, assigns this 17 and this 42. And, G over here does something similar, but for E4 and E3. And we'll make f and g non-adjacent to each other if f sends E3 to the same value that g sends E3. In some sense, this means, they're not in conflict with each other, and we'll add edges between any 2 functions which are in conflict with each other in terms of this common edge. So that's basically what's going on here. Again, you should have in mind that the weird looking blow up of a CK graph cycle. And let's zoom in a bit more on what the structure of these things are. So in V1, let's fix our favorite integer a and just look at all the functions f which send E2 to this value a, and let's go over to V4 and look at our second favorite number b and look at restrict our attention to functions g which map E4 to this common value. So I'm just restricting to some proper subset of V1 and V4. And my claim is that the graph that these 2 special sets of vertices induce is exactly a co-matching. So why is that? Well, once I tell you that all the f's here have ET equal to a, f is a function. F is determined by 2 things: what it sends f2 to, and what it sends what it sends E2 to, and what it sends E1 to. So because I specify what E2 is, it's now completely determined by some integer from 1 up to n to the 1/2, which is what it sends E1 to. And similarly, the g guys down here are determined by exactly what they send E1 to. And so basically we have some bipartite graph which has n to the 1/2 vertices here, n to the 1/2 vertices here, and moreover we'll have a non-edge between 2 things if and only if, and also the vertex sets are indexed by integers from 1 to square root n. And 2 vertices will be non-adjacent to each other if and only if they have the same index, i.e. if they send E1 to the same value. And this is just the definition of a co-matching of size square root of n, because we have almost every edge between these 2 parts, except we have for each vertex a unique non-node, namely the one which agrees with it on E1. So if we fix any given value on both sides for E2 and E4, we're going to find a co-matching. So kind of what this is saying is that the edge set between two parts is basically just some weird interwoven mess of co-matching. So somehow this construction is still intimately related to these co-matching constructions that we naively came up with before. All right, so this is a fine definition to make for a graph, but the key thing we want to use is that these have many KMIs. Specifically, for any function f from the edge set of the graph cycle to the integers from 1 to n over square root of n, then the set I consisting of functions f, which agree with this larger function capital F, we claim that this forms a KMIS. So for concreteness, let's look at this big F function being identically 1, since every edge of the graph cycle, in this case C4, to 1. So what is I? Well, in particular, I contains the function F1, which is in capital V1 and which sends E4 and E2 equal to 1. Because this function F agrees with this big F. Similarly, it contains F2, which sends E2 and E3 equal to 1. And more generally, each blob has a unique function F, which agrees with capital F. So the claim is that this is, so clearly this set has K, and we want to prove it's maximal independent set. First, it's an independent set because we look at look at F1 and F2, for example, they agree on E2, which means that they are non-adjacent to each other by definition. And similarly, all the other possible edges are not there. So that gives that this is an independent set. To show this is a maximal independent set, consider any new vertex G, maybe it's in capital V3 that we might try and add. Well, because G is distinct from F3, it has to send either E3 to something other than 1 or E4 other than 1. In the former case, G will be adjacent to F2 because they disagree on what E3 should be. And otherwise, it's adjacent to F4 because they disagree on what E4 should be. So we conclude that no such G can be added and maintain that we're an independent set. So indeed, this is a maximal independent set, proving this limit. All right, so now we're almost at something. So now we just make a couple observations. First, these blow-up constructions have exactly kn vertices because they have k blobs, and in each blob, it just consists of all functions from a 2-element set to a set of size n to the 1/2. So each blob has size n. Moreover, there are at least n to the k over 2 KMISs. That's because there are at least that many there are exactly that many functions from the whole edge set of CK to the first n to the 1/2 integers. And with our previous lemma set, each of these defines a distinct KMIS. And moreover, all these graphs would be triangle-free provided we're looking at a cycle of length larger than 3. And that's because all of these graphs are the subgraphs of blow-ups of the underlying graph CK. And CK is triangle-free for k greater than 3. And putting all of this together, we conclude that for k greater than or equal to 4, the maximum number of KMISs in triangle-free graphs is at least n to the k over 2, where here we do not have a floor like we did when we were making the co-matching construction. So indeed, this co-matching construction is not optimal. You can do better, at least when k is at least 5 and not. And so this is kind of a weird-looking construction. And you can ask, to what extent can you push this farther? And we can, in some regards, generalize this in 2 different ways. So firstly, the fact that we were working with a graph CK wasn't that important. You can start with any k vertex graph H and a fractional matching M of H. And if you don't know what a fractional matching is, just pretend this is a matching. For these 2 parameters, H and a fractional matching, we'll let GNHM be a k-partite graph whose parts are indexed by vertices of the base graph H. And the vertex sets are going to be all the functions f, which map edges containing the vertex u to the integers from 1 up to n to the fractional weight of e. And we'll make 2 functions adjacent to each other if and only if there's an edge between their corresponding vertex sets back in the base graph H. and if on this common edge, F and G disagree on the bound. So the main example to keep in mind is that this definition is exactly the same as if we take H to be CK and M to be the fractional matching with just a half on every edge, then this exactly recovers the definition we had before, and in particular, when H equals C4, this is exactly the pictures I was drawing. More generally, if H is an even cycle, then we can take M to be a perfect matching, and if you unwind what these definitions are saying, then this just corresponds exactly to a disjoint union of K co-matching. So this definition gives us a common language to talk about the co-matching construction and for this weird cycle blow construction. And moreover, it actually gives us a way of interpolating between these two. So for any, you can interpolate between the fractional matching, which is a half everywhere and which has value 1 on half the edges. And as you do that, you smoothly interpolate between these constructions of disjoint union of co-matching and this weird interweaving thing here. And again, these kind of examples show that the co-matching really is at the heart of all of these constructions. They're all hidden away somewhere here. So yeah, you can do this in a fairly wide generality. In particular, if you start with H a K vertex triangle free graph and M a fractal matching size K for 2, then this blow up construction will have about n vertices. It'll have at least n to the K over 2 distinct KMISs, and it'll be triangle free provided H is, again, because this is a subgraph of a blow up of H. Thus, all of these constructions give a new way to prove this lower bound of n to the K over 2. And further, if one suspects that this n to the K over 2 lower bound is best possible, which we kind of do, then it shows that there are many, many different looking constructions which achieve this. And because of this, it may be difficult to prove that this is a tight bound in general. Okay. So that's one way you can generalize this. You can start, instead of looking at graph cycles, you can look at arbitrary graphs. But you can also generalize this, instead of looking at graphs, to looking at hypergraphs. And I'm not going to go into too much detail with how exactly this is done. Basically, the idea is you start with some hypergraph H, and so before what we were doing is we start with some graph G, and then we made a blow up where between any two, where whenever there was an edge in our base graph H, we made some weird interweaving of co-matching. Here, if we're working with, say, a 3 uniform hypergraph, every time we see a hyperedge now, we replace that with some weird interweaving of the Ruger-Semrad construction. And more generally, for an R uniform hypergraph, we'll replace it by each hyperedge by a weird interweaving of Gowers-Leander type construction. Again, the definitions are very similar to what we have for the graph case, but for simplicity, I'll just omit it and hope you believe me that things work out. In particular, what you can prove is by working with H, a tight cycle, and taking a blow up of this tight cycle, then you can prove that for K, sufficiently large in terms of T, you can get a lower bound on this MT and K function, which is the same as the previous bound, but now once again, we've managed to get rid of that pesky floor function. So we have once again been able to improve our lower bounds. And in total, we think that these lower bounds are essentially best possible. So in particular, for all fixed K and T, we think there should be an upper bound of roughly n to the T minus 2K over T minus 1. And moreover, it might be the case that for small k, that you can get a stronger upper bound here using a floor instead of just this much either. And in total, this conjecture in full would be best possible up to the low 1 terms due to these constructions that I mentioned up to this point. But despite us, so formally we conjecture this. Personally, I think this is also probably true, but we didn't formally put it in. I just wanted to put this all in one box. So in general, we do not have any clue if this is actually true or not, but we do have some partial results. So a very simple result you can prove is that this bound is best possible when K is smaller than T. In particular, you can get something like this, which is just n to the k minus 1 here in this range of parameters. And you can prove this by induction, more or less. First of all, it's easy to prove that the number of 1 MISs in a KT3 graph is at this t. It's actually slightly smaller. And then given this, you can inductively use that the number of KMISs, maximum number of KMISs, is at most roughly n times the number of k minus 1 MISs in an n vertex KT3 graph. And why is this? Well, you can count the number of KMISs by going through each vertex and asking how many KMISs are you. And your favorite vertex V, the maximum number of MISs it's in is at most what the number of MISs in the graph after you delete it and its neighborhood. Every KMIS containing a given vertex V is a k minus 1, comes uniquely from a k minus 1 MIS after you delete that vertex and its neighborhood. So that was a bit of a mouthful, but in any case, it's not hard to prove that something like this is roughly true, and from this it follows here. And I'll note that this is not literally true because this m function is not monotone in n. If it were, this would be literally true, but it's not quite. But it's close enough that we can get this. But that's that. Right. So that dealt with k less than t in general, and zooming in on the triangle-free case. As I mentioned earlier, if k is at most 4, we know that this upper bound of n to the 4k over 2 is best possible. And some of these cases are somewhat straightforward to prove. For example, when k is at most 2, this is exactly the case that I discussed on the previous slide, so that's easy. If we happen to already know the k equals 3 case is true, then the k equals 4 case would follow immediately from, again, this relation that the number of 4 MISs is at most n times the number of 3 MISs. And with all this in mind, the only work we really need to do is prove this result when k equals 3, and then we'll have the full thing. And I won't go through all the details here, but let me try and sketch some of the key ideas. So if G is a k-partite graph, we'll let TGK denote the number of transversal MISs of G. Namely, these are the MISs which use exactly one vertex from each of the k parts of G. And a lemma we have is that for triangle-free graphs, you can find an induced subgraph G prime of G, which is k-partite and such that its number of transversal KMISs is at least a constant, depending on k, times the number of KMISs of G. And basically what this is saying is that up to constants, determining M3 and K, it's sufficient to determine this for k-partite triangle-free graphs, and moreover, we only have to count transversal MISs amongst such graphs. So that'll greatly simplify, our search space and trying to argue certain things. And in particular, will be done once we prove the following lemma, which is that we have an n-vertex triangle-free graph, which is 3-partite, then it contains at most n transversal MIS. And again, I won't go through all the details, but one particular claim that I want to highlight is this guy here, which is basically the main claim of this whole lemma. And it says, if you look at any vertex U in big U, which is in at least one transversal MIS, then there exists unique sets SU and TU, which are subsets of big U, such that whenever you have an MIS UVW with vertices coming from their corresponding parts, then the neighborhood of each of these V vertices into capital U is exactly this SU set. And on the W side, it's exactly this TU set. So again, all of these, 3 or 4 vertices in this capital V side, maybe they're in, let's say they're in some MIS with U, then, magically, they all have the property that their neighborhoods are exactly the same, at least with respect to looking at capital U. And, exact same pictures going on here with capital W. So this claim isn't terribly hard to prove once you know it's something you want to prove. Discovering, that this statement is useful or plausible is perhaps not obvious. Yeah, this is kind of the workhorse for this entire lemma. And in particular, I'll note that this is the only place where we use that G is a triangle-free graph. And it's important that we do that at some point in our proof, because this lemma is false if we delete the words triangle-free. In particular, the Rouget-Semery construction is a three-parted graph with much more than n transversal MISs, but it's very far from primary. And we have to use that hypothesis somewhere, and this is where we end up using it. Okay, so with this in mind, let's go through a bit more of the details. So for any set S, we'll let V of S denote the set vertices V in capital V, whose neighborhood in U is exactly the set S, and similarly defined W2. And we'll let U greater than or equal to 2 be the set of vertices which are in at least 2 transversal MIS. So then the next claim is that the number of transversal MIS using vertices in U greater than or equal to 2 set is at most this sum here. And really what this is saying is that for each individual vertex U in this set, the number of transversal MIS it's in is at most the minimum of these two quantities. In particular, it's at most this, and it's at most this. So why is that? Well, for each vertex U, the only vertices in capital V which it could form an MIS with is exactly this V of S U set. By the previous claim, every vertex in an MIS with U must belong to this thing. And the claim is that each of these vertices is in at most one 3 MIS with little u. And indeed, if we're looking at MIS containing, say, this bottom vertex and this vertex here, the third vertex has to be some vertex in W, which is non-adjacent to both of these. If there were 2 options for that, then when we add 1 in, that's not going to be a maximal independent set, because we could add the second one in as well. So in order for this to be a maximal independent set, there can only be one possible option. So for each of these vertices in VSU, they're in at most one MIS with little u. And similarly with on the W side, so in particular, both of these are upper bound from the number of 3 MISs containing this little vertex here. So okay, we have this sum here that we want to upper bound, and I claim that we can, for each of these terms, you can use either the trivial upper bound of this or the trivial upper bound of this, and you can do this in a clever way, such that when you for each term in the sum, after using these bounds, this term, for example, appears at most once, and this term appears at most once in the sum, and so on and so forth. So this is not an obvious fact. In particular, this, SU could be the same as SU prime, could be the same as SU double prime, and so on and so forth. So this individual term in the minimum could appear 100 times. And if this was true for every, all the W's as well, if every term here showed up in at least 100 minimums, then you couldn't do something like this and get each term appearing at most once. Each would have to appear at least roughly 99 times. But it turns out that because of the extra structure that's going on in this problem, you can replace, you can make it so that V of SU appears at most once and W of TU appears at most once, even if they appear in multiple minimums. So using this claim, we get that this sum here is at most the sum over all possible V of S terms and all possible W of T terms, again, because each appears at most once. And this quantity here is actually exactly equal to the size of V, because this partitions the vertices of V, and similarly this partitions the vertices of W. So we get an equality there. And this deals with, so if you unwind things, this sum here with an upper bound for the number of MISs using vertices here. So that gives an upper bound of this for the number of such MISs. So there remains to deal with those MISs using vertices which are not here. But by definition, any vertex which isn't in here is in at most one MIS. So the number that we miscount by is just the size of the vertices we're missing, which is at most the size of U. So adding that in here exactly gives the bound that we're looking for. Okay, so with that, I want to talk a bit more about some open problems, of which there are many. Perhaps the simplest open problem we have is the following. You have an n vertex triangle-free graph. Claim that the number of 5 MISs it has is at most n to the 5 half. And we have some partial properties on this. So we have a result which says that if you have an n-vertex graph, which is a subgraph of a blowup of C5, then this graph G contains at most n to the 5 halves 5m. In other words, if G is some subset of this looking graph, then it's not a counterexample to this conjecture on the previous slide. And kind of what this is saying is that if you believe that this conjecture was false, that there exists something that has many more 5MISs, then you shouldn't look for blow up constructions of C5, because any blow up of C5 will have at most this many 5MISs. And in particular, this GN C5 a half construction, this blow up construction I mentioned before, is the best we can do up to constants for MISs, which are for graphs which are subgraphs of the flows of C5. And kind of a natural extension to this thing here is to look at blow-up graphs of k-vertex triangle-free graphs H, in which case we believe it should be the case that such graphs should contain at most n to the k over 2 k-MISs. We'll note that it's not hard to prove this for H a cycle. You can basically just mimic this exact proof, and that'll go through. It's pretty easy to prove this when H is bipartite. But one interesting open case is when H is the Peterson graph. Is it the case that if G is the subgraph of a blow-up of a Peterson graph, does it have the most n to the 5, 10 MISs? So yeah, that's here. And I'll lastly, before I move on here, note that we actually have a slightly stronger version of this proposition, which says if G is a subgraph of this, or if it has, and it may have also some edges here and some edges here. So we can say something slightly stronger than that, as long as G is also triangle-free and a subgraph of this sort of graph. Then we have the same sort of graph. Again, if we're not triangle-free, then root of semi-check construction will show that this will not hold. And another kind of wimpy conjecture is that for k sufficiently large, this M3nk function is at most n to the k minus 3. And the real conjecture we have is that this function should behave like n to the k over 2. But right now, the only non-trivial upper bound we have is n to the k minus 2. This here is, a bit of a jump, and we don't know how to make it, but still we believe you should have much, much larger room for error here. It's kind of sad that we think this is the real answer, but when k equals 1,000, it's just magnitudes of magnitudes difference between what we think is true versus what we actually can prove, and what's still open. So we think maybe you can leverage. The idea here is that maybe you can leverage that k is very large to somehow get some extra, maybe using some Ramsey type arguments. So moving on from triangle-free graphs, you can look at KT-free graphs, and one particular interesting open case there is for MISs of size T. In this case, we basically conjectured that the answer is n to the t minus 2, or at least that's what I think. We never formally conjectured it, but this is kind of what I suspect to be the case. And there's some reason to look at this particular problem. For one, if you could prove this is true, then you also prove that not only you prove type bounds here up to little o1 terms, but in fact you prove type bounds for any k less than 2 times t minus 1. And what this says is that, and this is exactly the range where we only have a lower bound in terms of the floor. Beyond this k, we can start improving our lower bound without a floor in the exponent. So if this is true, then in fact the range where we have floors is exactly correct. So that would be nice philosophically to know. I'll also note that we know this is literally true for t equals 3. This is that upper bound proof that I sketched a few slides ago. And it may be possible to extend the ideas we have for that argument to keep t-partite KT-free graphs. If you want to do this for general KT-free graphs, which is kind of the main thing we want to look at, you're going to have to add in a couple extra ingredients for sure. But at least for t-partite things, I think if you figure out the right generalization, it should be a fairly smooth transition. But non-t-partite may take some extra work. And another kind of philosophical question that I'm interested in is to what extent these little O1 terms are necessary. So for our KT-free graphs, anytime we're using roots of Semirate or Gauger's answer, we always have these little O1 terms appearing in the exponent. And the question is, are these really necessary? And like the simplest case of this is for 3 MISs in K4 free graphs. Can you have at most n squared minus little O1 3 MISs? And it's not hard to prove this is true if G is tripartite, then it has at most this many 3 MISs. And the proof is basically the same as the lower bound. You take like a tripartite complement of our base graph, and then you can more or less reduce the problem to Rouge's Semirate. So in fact, in this case, the little one here is exactly the same little one function that shows up in the Rouge's Semirate problem. And it's not known in general what this little one is. That's still kind of a major open problem. But whatever it is, it's the same thing that's showing up in this MIS problem.